Hello, and welcome. Today, we're going on a journey inside a classic piece of engineering that you've likely seen but maybe never fully understood, the analog meter. We're talking about those instruments with a physical needle that gracefully sweeps across a dial to show a measurement. The technology behind them is both brilliant and beautiful in its simplicity. We will be exploring the inner workings of the most common type, known as a permanent magnet moving coil instrument, or PMMC for short. By the time we're finished, you'll not only understand what each part does, but you'll also appreciate the clever physics that makes it all work so perfectly. Let's begin by looking at the stationary parts, the foundation of the entire instrument. First, we have the permanent magnet. You can see its two poles here, labeled north and south. A magnet creates an invisible area of influence around it called a magnetic field. Think of it like the Earth's gravity, but for magnetic objects. This permanent magnet's job is to create a strong, constant, and unchanging magnetic field in the space where the action happens. The term permanent is key. It means this magnet works all on its own, without needing any electricity. Now, look at the piece situated right in the middle of the magnetic poles, labeled core. This is a cylinder made of soft iron. The soft iron core is a crucial component. Its purpose is to concentrate the magnetic field. You can imagine the magnetic field lines as invisible threads stretching from the North Pole to the South Pole. The soft iron core acts like a superhighway for these field lines, attracting them and guiding them through the center. This makes the magnetic field in the gap much stronger and, more importantly, it shapes the field in a very specific way. This special shaping creates what we call a radial field. Imagine the spokes of a bicycle wheel, they all point directly from the rim towards the center hub. A radial magnetic field is just like that. The field lines are always pointing straight across the gap, perpendicular to the coil's motion. The reason this radial field is so important is a secret we'll uncover in a little bit, but it's the key to making the instrument accurate and easy to read. So, to recap the foundation, we have a permanent magnet creating a powerful magnetic field, and a soft iron core concentrating and shaping the field into a perfect radial pattern. Now, let's move on to the heart of the instrument, the part that actually moves. This is the moving coil. It consists of a very fine, insulated copper wire, wrapped around a lightweight rectangular frame. This frame is called the former. The former is typically made of aluminum. It acts as a skeleton, giving the coil its shape and rigidity. The current that we want to measure is passed through this copper wire. The more turns of wire in the coil, the more sensitive the instrument becomes. Of course, for this coil to move, it must be able to rotate with almost no resistance. If there was friction, the measurement would be inaccurate. This is where the pivot and jewel bearing system comes in. At the top and bottom of the coil assembly, there's a tiny, hardened steel cone, called a pivot, which rests inside a small, cup-shaped jewel, often a synthetic sapphire or ruby. Imagine trying to spin a top on a rough surface versus on a smooth piece of glass. The jewel bearing provides an incredibly low friction surface, allowing the entire coil assembly to rotate almost effortlessly. It's a technique borrowed from high-precision watchmaking. So now we have our moving coil assembly, poised on these jewel bearings, sitting inside the powerful, radial magnetic field. This brings us to the physics of how it all works. When an electric current, specifically, a direct current or DC, flows through the coil's wires, a magical thing happens. A fundamental law of physics, sometimes called the motor principle, states that a wire carrying a current within a magnetic field will experience a force. Because the wires on opposite sides of the coil have current flowing in opposite directions, one side gets pushed up, and the other side gets pushed down. This pair of forces creates a turning or twisting effect on the coil. This turning force is called the deflecting torque. The word torque is just a scientific term for a rotational force. The more current that flows through the coil, the stronger the magnetic push, and therefore, the greater the deflecting torque. But if that was the only force, even the tiniest current would cause the coil to swing all the way to the end stop. We need a way to control this motion and make it proportional to the current. That is the job of the spring. You'll see a delicate spiral spring attached to the moving assembly. There are usually two of them, one at the top and one at the bottom. As the coil rotates due to the deflecting torque, it winds these springs up. Just like a twisted rubber band, the springs want to unwind and return to their resting position. They generate an opposing torque, a restoring force, which we call the controlling torque. The further the coil turns, the tighter the springs get, and the stronger their controlling torque becomes. The coil will stop rotating at the exact point where the turning force from the electricity, the deflecting torque, is perfectly balanced by the unwinding force from the springs, the controlling torque. Think about it, a small current creates a weak deflecting torque, so the coil only turns a little before the spring's force is strong enough to stop it. A large current creates a strong deflecting torque, causing the coil to turn much further before the springs can balance it. This beautiful, elegant balance is what makes the instrument work. And here's another piece of brilliant design: these springs also do a second job. They are the very conductors used to carry the electric current to and from the moving coil. Now, all this movement is useless if we can't see it. This leads us to the display system. Attached to the moving coil is a long, lightweight pointer. As the coil rotates, this pointer sweeps across a fixed scale. The scale is the arc printed with numbers and lines that represent the units we're measuring, like amps or volts. During manufacturing, this scale is carefully calibrated so that the pointer's position accurately reflects the amount of current. Remember the radial field we talked about? Here's where it pays off. Because the magnetic field is uniform and always at a right angle to the coil, the deflecting torque is directly and linearly proportional to the current. This results in a linear scale, meaning the markings are evenly spaced. The distance between 1 and 2 amps is the same as the distance between 4 and 5 amps. This makes the meter incredibly easy and intuitive to read. To ensure the most accurate reading possible, high-quality instruments include a mirror on the scale, right beneath the pointer. This is to combat something called parallax error. Parallax error occurs when you view a needle from an angle, making it appear to point to a different value than it actually is. Think of looking at a car's speedometer from the passenger seat. To use the mirror, you move your head until the reflection of the pointer is hidden directly behind the real pointer. When they are perfectly aligned, you know you are looking at the scale from a perfect 90-degree angle, eliminating any parallax error and giving you the true, precise reading. Finally, let's look at the small but important details. You'll notice small weights attached to the assembly, labeled balancing weight. The entire moving system, the coil, the former, and the pointer must be perfectly balanced. If one side were heavier, gravity would pull on it and affect the reading, especially if the meter wasn't perfectly level. These counterweights are carefully adjusted so that the assembly is gravitationally neutral, ensuring that only the magnetic force is responsible for the pointer's movement. One last concept is damping. When a current is applied, we want the needle to move smoothly to the correct position and stop. We don't want it to overshoot the mark and then oscillate back and forth like a pendulum. This calming effect is called damping. In a PMMC instrument, damping is cleverly achieved through the aluminum former. As the conductive aluminum frame moves through the magnetic field, it generates its own tiny electrical currents called eddy currents. These eddy currents create their own magnetic field that opposes the motion, acting like a brake. It's like moving your hand through water. The water resists your motion, making it smooth. This ensures the pointer glides to its final position quickly and decisively. So, let's summarize the entire process from start to finish. First, a direct current is passed into the instrument, flowing through the springs and into the moving coil. Second, the interaction of this current with the permanent magnet's field creates a deflecting torque, causing the coil to rotate. Third, as the coil rotates, the control springs wind up, creating an opposing controlling torque. Fourth, the coil and its attached pointer stop moving at the exact point where the deflecting torque is perfectly balanced by the controlling torque. And finally, the position of the pointer on the calibrated, linear scale gives us a visual, accurate reading of the current. From the powerful permanent magnet to the delicate jewel bearings and the elegant balance of forces, the permanent magnet moving coil instrument is a masterpiece of electromechanical engineering, a device that turns invisible electricity into a visible, understandable measurement. Thank you for joining me on this detailed exploration. I hope you now have a new appreciation for the ingenuity packed inside these classic analog meters.